Hi, we're Team 4 in Section 11 from ME435. This video walks through our autonomous vehicle final project. We'll cover what we learned across Labs 1 through 3, present our flowchart for combining everything, and then demonstrate our team-defined task showing the robot drive autonomously from point A to point B, following the shortest distance. Across the 3 labs leading up to this project, we covered 5 learning objectives. We'll go through each one briefly. Objective 1, Basic Robot Control and Kinematics. In Lab 1, we learned how the JetBot's 2 motors translate into motion. We measured how motor power values map to wheel angular velocities and used those relationships to drive the robot through straight segments and 90-degree turns. The key result was a tuned set of motor commands, roughly 0.12 motor value for forward motion at our calibrated speed, and plus or minus 0.06 on each wheel for a 2-second timed 90-degree rotation. These values are the building blocks for any motion the robot makes when it can't rely on visual feedback. For example, executing a turn at an intersection where the lane line has disappeared. Objective 2, Sign Recognition. Lab 2 introduced sign recognition. The original lab walked us through training a deep learning classifier on the categories stop, speed, and no sign. The captured images served as a reference to match the environment with the predicted sign in real time. These signs can then function as inputs that influence the JetBot accordingly. Objective 3, Path Following using image processing. Path following uses the JetBot's onboard camera to track the yellow dotted line in the center of the road. The pipeline: convert each frame from BGR to HSV color space. Mask for yellow pixels using our calibrated HSV thresholds shown. We then apply a Gaussian blur, crop to a region of interest at the bottom of the frame, run canny edge detection, and use a Huff line transform to find the line segments. The average exposition of those segments gives us a target point, and we feed the angle of offset into a PD controller.
Objective 4 focused on using the camera bot and JetBot together so the JetBot could localize itself on the roadmap. The JetBot communicated with the overhead camera bot through SSH networking. The camera captured an image of the roadmap from above, and the JetBot used an image to detect the April tag mounted on top of it. After applying the calibrated camera matrix and distortion correction, the April tag detection gave the JetBot's position and heading angle on the map. This later functioned as our starting point A in the path planning process. Objective 5 focused on generating a path planning map that the JetBot could use to decide where to go next. We first converted the overhead map image into a binary occupancy grid, where the drivable road was shown as white and obstacles were shown as black. Then we generated a probabilistic map by randomly placing accessible nodes on the drivable road and connecting them into possible paths. The algorithm then searched to find the shortest path from the JetBot's current position to the selected goal location B. After generating the path, the final step was to guide the JetBot to an intersection using the next node on the path. The next node was transformed into the robot's local frame, and the angle to that node was calculated using arctan. Based on our logic, if the angle is within a 20 degrees range, the JetBot goes straight. If the angle is greater than 20, it makes a turn left, and if the angle is less than minus 20 degrees, it makes a turn to the right. In our case, the calculated angle was very small, so the correct output was straight as shown. Here's how all 5 objectives come together to find the shortest path in our chosen subtask from point A to point B, as shown to the left. In the right, the flowchart shows as startup the system runs a one-time initialization, the JetBot connects with the camera bot, asks for an overhead photo, and runs April tag detection to find its starting position and heading. That same photo gets converted to a binary occupancy grid, and a probabilistic roadmap finds the shortest path from start to goal. Then the main driving loop begins. The JetBot's onboard camera streams frames continuously. For each frame, we run the path following pipeline, HSV mask, edge detection, hue lines, and PD controller, and feed motor commands directly to the wheels. This continues as long as the robot can see the yellow lines. The stop sign detector runs in parallel on every frame. If enough red pixels appear in the camera view, the robot stops for 3 seconds, then resumes. When the yellow line disappears for longer than a brief grace period, we treat that as an intersection. The robot stops, asks the camera bot for a fresh photo, runs April tag again to update its current position and heading, then computes the angle to the next path node, and converts that angle to a steering decision. The kinematics from Lab 1 then execute the actual turn 2 seconds of opposite wheel motion for a 90-degree turn, or a brief nudge for a go straight decision. After that maneuver, the robot creeps forward slowly until the lane follower picks up the next yellow line, and normal driving resumes. This loop continues until we reach point B.
For our team-defined task, we chose to demonstrate autonomous navigation from A to B while using line following, path planning, and real-time position detection using AprilTag, combining 3 of the 5 objectives into a single run. First, I'll talk about what we set up. Point A is here in the left middle road of the map, and point B is in the bottom. In the demonstration, we first use the SSH to call the camera bot, and the overhead photo comes back. AprilTag detection identifies our robots at coordinates around 124, 260 in centimeters, with a heading angle near 273 degrees. PRM runs and produces the shortest path from point A to point B. Then we run it and the robot starts driving. The PD controller is used to follow the yellow dotted line. After one turn, the robot reaches the intersection. The yellow line disappears because of this, and the robot must use AprilTag position detection. The camera bot sends a new photo, AprilTag updates the position, and the system computes the angle to the next path node in the calculated path. We're computing the angle from where we are to where we need to go, and turning whichever direction makes that angle smaller. In this case, that works out to roughly a negative 90 degrees in the local frame, and the decision is to turn left. The path following is then used to execute that turn, and the robot creeps forward until it again sees the yellow line on the new road and follows that again. The robot continues lane following, hits, and then continues straight until it reaches at point B. Next time we have a few things we'd improve. First, we did not use kinematics. This would have made the turn at the intersection much smoother. Second, we did not use sign detection. We were unable to figure out how to implement it while everything else was still running. We believe it was just too much at once, and we would need to reduce our current code. That is all for our autonomous vehicle final project. Thank you for watching, and thank you to the TAs for the support throughout the lab.